Okay, so for section 5.3, let's take a little look at this first section here. All right, so Niels Bohr established the concept that we had fixed energy levels outside the nucleus, which they generally call atomic energy levels. And Bohr knew that they needed to be there, but he didn't know why. And we had a French aristocrat by the name of Louis de Broglie, who actually earned a degree in history, came around and said that if waves behave like particles, is it possible for particles to have wave properties? So what he did was he proposed that matter was wave-like, and he suggested a reason as to why we would have these fixed energy levels outside the nucleus. So I'm going to skip over quite a bit of this. But there's a couple things that I want to make note of. Turn to the next page. De Broglie had derived an equation to calculate the wavelength of a particle, and he combined Albert Einstein's equation, E equals mc squared, with Max Planck's equation to get, let's go to the next page. Derivation isn't necessary. He got this equation here. The wavelength is equal to h, Planck's constant, divided by m times v. So this equation is significant for a couple of reasons. This equation tells you that any moving particle, like a baseball, a football, or an electron, has a wavelength that we can actually calculate. And if you take a closer look, mass is in the denominator of the fraction, so that means that mass and wavelength would be inversely related. So that means the smaller the particle mass, the larger the wavelength you will calculate. So that means things like electrons, which have masses so close to zero that we say they're zero, would have a huge wave-like property. Okay, so it says a particle's wavelength is inversely related to its mass. So as mass decreases, wavelength increases, and vice versa. Okay, so a mass as small as an electron will have a wavelength that is extremely significant. So I can't ignore the fact that electrons have wave-like properties, but I could ignore the fact that a baseball has wave-like properties because it's so large. Okay, now you may be asked to calculate the wavelength of something, and let's go on to, I'm not going to calculate anything with you, it's not really necessary right now, but let's go on to this concept called particle-wave duality. Particle-wave duality basically says that something can behave as a particle but have wave-like properties. This pertains to electrons. Let's go to the next page. I'm skipping a lot of this just because it's not really relevant to what we're going to be doing. Louis de Broglie won the Nobel Prize in Physics in 1929. I want to look at this right here. If you're using de Broglie's equation to calculate the wavelength of something, h is Planck's constant. M would be the mass, and then you may want to make a note that because Planck's constant has a mass unit of kilograms in it, you would need to then have your mass be in kilograms. And then V would be velocity. Okay, so I'll do one problem with you. Let's take a look at the practice problems at the top of the next page. God bless you. Okay, Number 1 says, calculate the de Broglie wavelength of an alpha particle with a mass of 6.64 times 10 to the negative 27 kilograms, traveling at 16,000 kilometers per second. Okay, so wavelength equals Planck's constant divided by mass times velocity. So 6.626 times 10 to the negative 34 kilogram times meter squared per second squared, all over the mass times the velocity. Now, your velocity needs to be in meters per second so that it can cancel with the units in Planck's constant. So this is 1.6 times 10 to the 7th meters per second. I'm just giving that to you. We know how to do one-step metric conversions. And then you would end up with 6.2 times 10 to the negative 15 meters. They will sometimes ask you for those units in like nanometers. Okay, so you may be converting meters to nanometers in a one-step metric conversion, but we're just going to leave that as it is, okay? And there are other equations that you can sort of incorporate here, but we're not going to do any of that, all right? Okay, now, I just need to mention like a couple things, and then we're done with this section. I'm not assigning homework for this section, okay? Okay, let's come down here. So not everybody was comfortable with the idea that electrons could both be particles and waves. There were two competing scientists that had different mathematical theories. We had Werner Heisenberg, and Werner Heisenberg said he was going to treat the electron as a particle. And then we had an Austrian physicist, Erwin Schrödinger, said the electron is not a particle. And then he decided to strictly view an electron as a wave. So they were competing with the math, but really their ideas came together into one theory, and they contributed to quantum mechanics. Let's take a look at the Heisenberg principle. If you try to find the location or where an electron is moving to, like its momentum, then simply trying to find an electron, like by shining light on it, which would be energy, is going to move it. Okay, so the Heisenberg uncertainty principle says that trying to find something on an atomic scale is incredibly difficult to do, because shining light or providing energy to help you find it will simply blow it away. So what they did was they used calculus to derive the probable locations in space of electrons, and they came up with something known as atomic orbitals. So atomic orbitals are the regions in space around a nucleus where electrons with certain energies are likely to be found. And this is what I'm going to be spending a lot of time on in the next section. Okay? All right, so that's all I'm mentioning from here. Let's turn to section 5.4.